Nice. Okay. And so let's start. Let's talk about chapter 9. Chapter 9 is all about alkynes, addition reactions of alkynes, or I guess just in general, different types of reactions that can take place with alkynes, whether you're building them, reducing them, extending them, changing them into an alkene, or I guess that's the part of reducing, or adding halide to them, halogenation, right? And so this big old like diagram here, it's very intimidating. When I first saw it, I was not with it. But as you go through the chapter and as you familiarize yourself with the different reactions, this starts to make a lot of sense. And it looks intimidating, but if you look at it, you have like the central thing. And like, for example, you can see how you could get to this geminal dihalide, and then or you can see how to get from this geminal dihalide to an alkyne, and this diagram will tell you the secrets, and so it'll be good to learn this because this one will also help you, but it's nice to have this visual, at least in the beginning, as a crutch, and then eventually start to solve problems without it, and then checking back at it to check if you're only to check after you've attempted to solve it yourself. And so before we do any practice problems, let's just first do some foundation stuff. Let's just talk about uh, just like simple basic stuff for alkynes that you should know, and that you will learn from the chapter, or I guess from this video if it's good enough. So let's start with creating your alkyne. Um, from, like, let's say you have an alkyne, but you can make this from, we just saw one example on that graph. You can make this from an alkene, or you can make it from, this is more chapter 10 stuff. You can also make it from an alkane. But let's talk about how you can make it from this alkene. So if you start with an alkene, and then you do the addition reaction of adding two halides, whichever ones of your choice in this solvent, we know that if we're adding these two, this gets removed inside of this solvent, and we end up with a halide here, and we end up with a halide here on either side of the bond. And then we can, from this, we can actually get to an alkyne by using this reaction. I guess we want it in excess. And I think you could get away with just using this, but what it usually looks like is this, and then two, or actually, yeah, this is the reaction you want. Never mind. You need first step and second step, and I'm going to tell you why later on. But for simplicity and just for understanding, this will remove this space. What it will do is, remember in chapter 7 and 8, when we had our alkenes and we had our hydrogens on either side of the bond, and then what would happen is, if our base took a hydrogen, this would act as a leaving group, and then we'd form one bond, and then this would take another hydrogen, this would act as a leaving group, and it would form another bond. But because this solvent is in excess, it will also take like a hydrogen that's sticking out from the terminal end, and what it will form is your alkynide ion. I think that's what it was called. And it's negatively charged. And then when you put it in the second solvent, water, what it does is it like reprotonates that end. And so this is the end of the arrow, pointing to a hydrogen. And then you end back up with your alkyne. Right, and so that's what this part, the first part does. First part will just like strip it of its hydrogens, and then the second part will reprotonate it, so that it's neutral or has no formal charge. Okay, and so that's how you can create an alkyne from an alkene. From an alkane, this is more like, this is touched on more in chapter 10. But essentially, what happens in chapter 10 is, let's say we have I guess like something like this, right? Something like this. what happens is you can take like I think like a single electron from this thing and you use like a hooked arrow, and then you can also take it from like something else, use a hooked arrow, and because you have like the two separate electrons, you form like a double bond or a triple bond, and that is like all with like the movement of the radical electron. And it's just you end up using the half arrows, but from two half arrows you can make like essentially one full arrow, one full bond. And that you can go more into detail in chapter 10. For now, and for the problems from chapter 9 and just understanding those reactions, we can just form an alkyne from an alkene, right? Okay, and so now let's also quickly look at reductions of alkynes. And this means you're going from two pi bonds or triple bond to a double bond, or an alkene, or you can even go as far as making an alkane from an alkyne. And this one's a little bit more straightforward. To get to an alkene, you can use one of two reagents. And so the first one is sodium metal and liquid ammonia. So this one will take us from an alkyne to an alkene, or you can use H2 and platinum, I think that is. And you can use either or if you just want an alkene. However, if you want to get specific and you want, let's say, a trans alkene, which is one that might look like this, with a group on one side and a group on the opposite side, if you put a line through it, you use this reagent. And then if you want one that is cis, right, where it has, if you put a line through it, they're both on this side, you can use this reagent. But if you don't care or you don't mind, or it ends up being an alkene that's at the end, then I guess either or will work fine. Okay, and now to get to an alkane is something actually, I'm sorry, this is not platinum. This is what we use to get to the alkane. I mixed it up for a reaction from the alkenes chapter 7 and 8, when we talked about addition reaction to alkenes. This actually uses something similar. It still uses the two hydrogens, but it uses a poison catalyst, or also something called like Lindlar's catalyst. I think it's named after the guy that discovered this. But essentially what happens is if you just have like H2 and what we had it previously, which was like, I think it was platinum or nickel, what happens is it doesn't just stop at an alkene. It's not like, oh, okay, we're at an alkene and it stopped. It will continue to protonate until it gets to an alkene. So it will continue to remove the bonds and add hydrogens until it just gets to this single bond. And we talked about it before, like why would you want to go from something that takes a lot of time and effort and it's expensive to make, and to something very simple and basic and cheap, essentially, I guess like energy wise and maybe even like money wise. But for the sake of this course, and the sake of our homework problems, we will happily do this if it gets us to the product or the starting material we want in synthesis or retrosynthesis. But I think we talked about it in class that in real life, this is probably not the most ideal reaction you want to go to. But yeah, and so what happens is this doesn't know to just stop at an alkene. It will continue to go until it hits alkane, unless you use a poisoned catalyst or Lindlar's catalyst. And they call it a poisoned catalyst because it will only act as a catalyst up until it gets to an alkene. And then it slows down or completely stops and does not continue to form the alkane. The major product is the alkene. And so that's nice. But yeah, so these are the three reagents we want to keep in mind for if we want to find or form trans alkene, or if we want to form a cis alkene, or if we just want to go all the way home and just make an alkane for alkane's sake. Okay, and then last thing I wanted to talk about is that we should have not problems yet. That looks like scare problem down there. Is alkylation. I think this is how it's spelled. And this is extending your alkyne, like making it something, maybe not this in particular, but making it something like that, or making it bigger, adding things to it. This is all called alkylation. And to do this, it's kind of simple. What you usually end up doing is let's say you have your alkyne, and you want to add something to it. So what you do is you want to remove the hydrogen here because you want to make it an alkynide ion. And how do you do that? Well, remember earlier on, if we add this, we can remove the hydrogens from the end there. And so once you have your, I think, alkynide ion, right, it's negatively charged, you can go ahead and add something like this, right? Which is just like ethyl and iodine. But what ends up happening is they separate, right? And this is our positive charge, this is our negative charge, and they get together and they connect. And so this will connect with that, with the ethyl part, and it can end up looking like this, right? And that's how you continue. You can even add like more intricate structures that we will see later on. And like I think all they do is just like literally add halide at the end of it. But yeah, and that's how you extend it, our alkylations. You add them together. Okay, but of course you have to deprotonate it first. I think that's what it's called, right? Okay, let's do some problems because that's the best way to learn. Whoopsies, I already did those ones. So we know that when each of the following alkynes is treated with sodium metal and liquid ammonia. So we remember this. We know it makes an alkene, and we know actually in particular it makes the trans alkene. And so what I like to start off with is counting my carbons, and so I've already numbered them here, 1 through 6, and then I want to make sure that I end with 6 carbons, and this will now start to have like a kink in it because it will reduce. And so what will happen is, I believe this will get like protonated and add hydrogens or something to both sides, and then we end up with something that looks like this. Let's make sure it has 1, 2, 3, 4, 5, 6 carbons, and then our double bond is going to be between 4 and 5. Perfect. And we know it's trans, and so if you cut a line right through it, it is trans. And so now let's do this one. This one is 1, 2, 3, 4, 5, 6, 7. Right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It has this here, that here. And then we have our double bond between 4 and 5. 1, 2, 3, 4, 5 here. And we know it's going to be trans because of the reagent we're using. And so we put a line through it, it's trans, perfect. And then let's just do this last one here. Like that. Actually, you can actually draw it like this. And this one is also trans. Okay, and let's just check our answers onto the side here. Perfect, nice. Yeah, and so this one, I kind of already drew it out. But essentially, you want to look here, and because you're going from an alkyne to a cis, right? If you draw a line on it, they're both on this side of the line, to a cis alkene, and we know we're going to need a catalyst to stop at that alkene, at the double bond. Same thing here. We look at the product, we see that it's an alkene, we see that it's a trans alkene, and we know that this reagent here will give us the trans alkene. And then if we go here, we have our trans alkene. We know this is the reagent that will go from an alkyne to a trans alkene. This one's tricky because it gets reduced all the way down to an alkane. But remember, if we just use the regular reaction that we used from chapter 8, this will just add hydrogens to both sides of the bond, but it'll continue to do it with the catalyst. The catalyst won't stop at any point, and then it will go all the way until it's down to an alkane. Okay, so now that we have that down pat, let's do some other problems. Here we go. Okay, so what we have here is excess HCl. And so our double bond, we know this is going to form, let's see what it looks like from the chart. Excess H of anything, it's gonna create a geminal dihalide. Something else to keep in mind too are these two things. Geminal means that both halides are on the same carbon, right? That's what geminal means. And you can think geminal, you can think is jammed, right? Because they're both on the side, on the same carbon. And then vicinal is when they're on different carbons or like adjacent carbons. And so it'll look more like this. And yeah, this is a carbon and this is a carbon, and they're separated. But okay, and so we know if we're adding excess of HX, we're gonna add that halide Markovnikov on the same carbon. So let's go all the way down here. And so we know it's gonna add them here, and it's gonna add two of them. So let's just redraw this out real quick. Let me just confirm this answer. Yeah, I think that looks right. Yeah. Looks good. Okay, and so now let's move on to this one. I think too, if you want to make it look even like better, you can do like one wedged and one dashed. But yeah, let's do this one. These are hard to draw for me. Someone said I make them look like houses. They're just so hard. And so this is already a dihalide. This is already a geminal dihalide. Now we're going to go to an alkyne from this. And how that works is, I think this first part, remember we used it earlier, this base will continue to take away hydrogens. So we know that there is a hydrogen here, and we know there's another one here. And so this will do its leaving group thing, and this base will take this hydrogen, and so this will form a double bond here, and then same thing, this will take a hydrogen, this will be a leaving group, and it'll form another double bond here. And then because this is a base, it will also take this hydrogen, and that's why you have step 2 here to reprotonate the end section. So let's redraw it out now. So it will now look like this. Ta-da! But I think because it's a triple bond, it just goes straight down twice, like that. Perfect. Okay, and the H2O is again adding the hydrogen to this end, because it would otherwise be negatively charged like that if we just had the first part of the reaction go through. Okay, let's do right. Okay, let's do 8, because this looks kind of familiar, because we have this bottom part from a reaction that we would normally see in like chapter 8. Let's do this. So let's look at this problem here. We have this reagent here, the sodium amide, or I guess like amine. This part of it will act as a base, like we usually do, and we know here there's a hydrogen, and we know here there's a hydrogen. We know there's probably like one more hydrogen connected here, and we know this is an excess, and so it will take this hydrogen, it will take that hydrogen, and it'll take that hydrogen. Then we have a leaving group here, and we have a leaving group here. And what ends up forming is we'll have two bonds form, right? Because missing chlorine, missing chlorine, missing hydrogen, missing hydrogen. However, because we have another hydrogen removed here, because this doesn't just like stop and it's like, all right, this is it, enough's enough. It'll continue to deprotonate in excess. And so what we'll have is the negative anion on this end. And so let's draw what our next step would look like. Something like that, right? And then it doesn't bend. And then it would also have this negative charge here. And then what would happen is water, let's actually draw it from this side. Water, we put this inside this reagent and the electrons here will protonate by grabbing hydrogen. Then you will have a product that looks like this. With no charge at the end. But then what happens is you're having HBr in peroxide. And remember what happens here in an alkene, right? You end up getting a bromine added to the less substituted side, or anti-Markovnikov. And so we know a bromine would get added here. But we also see that we have a hydrogen here. And so this, I believe this would get protonated on this side. And then what will result is the bromine gets added to that side. But let's draw it out. So you would end up forming an alkene with bromine. And you don't get rid of the other bond, because remember, we're going from an alkyne adding HBr and peroxide, and so only one of our bonds gets removed from here. But it can be, I think it can be added either cis or trans. Whoopsies. And so this can be a final answer, or your other answer can be this. Something like that, right? Or this can be your other answer. So either of these work. But yeah, that's crazy because we just learned this, and this is familiar to us. And so we applied each of them to the things. Okay, I'm going to end it here. I might try to do more problems, maybe like using different types of reaction, but I tried to use as much as I could from this table or this diagram here. All right, good luck.